Okay, so we've talked about one thing that you can do with a conductor in getting it to respond to an electric field is to charge it. But what happens if we take a neutral conductor and put it inside an electric field? And so here's my conductor, and notice I'm going to put it into a constant electric field. I know the electric field is constant because the spacing between my lines is uniform. Happens to be an electric field that points down. So one way to generate this kind of electric field is to say, well, I've got positively charged stuff up here, negatively charged stuff down here. So what happens is that, again, the free electrons within the conductor will move in response to the field. So my negative charges, right, the free electrons will move to this side of the conductor. That will leave an absence of electrons over to this side. And so that sets up its own electric field. So again, I've got positively charged things on this side of the conductor, negatively charged things on this side of the conductor. And so I've got the external electric field, the purple one that points down, but have generated an electric field within my conductor that points up based on how I've rearranged the charges in my conductor. And so what happens is that basically the charges continue to rearrange themselves on your conductor until the electric field reaches zero. And once that happens, then you've reached what's known as electrostatic equilibrium. So one important point to note is that for any conductor in electrostatic equilibrium, and again, whether it's charged or not, for any conductor, the electric field inside the conductor is zero. The charges will simply arrange themselves to make sure that the electric field inside the conductor cancels out. And this is true whether you've got a solid conductor or a hollow conductor. So there are several properties that describe conductors in electrostatic equilibrium. And so this is just sort of, hey, we talked about equilibrium in terms of all the forces and torques canceling out. We've talked about equilibrium in terms of thermal equilibrium, where things are at the same temperature. Here we're talking about electrostatic equilibrium, and sort of what defines electrostatic equilibrium is that the electric field is zero everywhere inside the conductor. And again, this doesn't matter about whether the conductor is solid or hollow, whether it's positively charged, negatively charged, or neutral. This is true always for a conductor in electrostatic equilibrium. If your conductor carries a charge, so again, this is true whether it carries a charge or not. If your conductor does carry a charge, then that charge is always going to reside on the surface of the conductor. And again, that doesn't care about whether the conductor is solid or it's hollow. That's where all the charge will be on its surface if it's in electrostatic equilibrium. The electric field near the conductor is going to have a magnitude given by this expression and is perpendicular to the surface. So basically, whatever shape your conductor is, if you zoom in close enough, effectively it's going to look flat. In the same way that if you think about from our perspective on the surface of the Earth effectively looks flat to us sitting on it because we're so close given the curvature of the Earth. Well, you can move close enough to any conductor so that it basically looks flat, and the electric field will point perpendicularly away from the surface, or away or towards the surface, depending on whether you have a positive or negative charge on the surface. And this will give its magnitude. And this symbol here is called, it's sigma, and we use it for the surface charge density. This is a way of saying charge per area. Epsilon naught, we've seen before, we know that this is related to our Coulomb's constant, and so this is our 8.85 times 10 to the minus 12 is what its value is. So get close enough to any conductor, and this is what the electric field is going to look like. If you do have an arbitrarily shaped conductor, so a conductor where their curves, their flat regions, curved regions, whatever. You're going to have the strongest electric field where you see the largest curvature. So part of what that means is a place where your conductor has a lot of curvature. It's pointy, right? It's not flat here. It curves very quickly. That means that basically more charges will be able to collect within that curved region than it will over the flat region. And so you'll end up with a larger surface charge density and a stronger electric field. So these are just sort of the way it works when you put conductors into an electric field and then let them reach electrostatic equilibrium. And so the picture that's actually very useful here, and again, think of this as we've got some positive charge up here that's generating our electric field. We've got negative charge down here, and now notice that what you see is the electric field inside our conductor is zero because the free electrons within the conductor have rearranged themselves on the surface so that the electric field cancels out. And you see that that's caused the external field to change its shape. So instead of just running straight up and down, now it's responding to the charges on the surface of the conductor. And here's where you can see that basically each of these lines comes into the sphere perpendicular to the surface. So here's the normal to the sphere at this point basically runs in this direction, and that's the direction that the electric field line comes in. This is the negatively charged side of the sphere. So again, we've got lines coming away from positive charge into negative charge, and then on this side they go away from positive charge into the negative plate sitting over here that's creating my external field. So this is simply the behavior we see with conductors when we put them into electric fields and how they respond once they've reached electrostatic equilibrium.